Hello students, this is Dr. Anita, Geochemistry mentor, welcoming you for another session in aldehydes, ketones and carboxylic acids. In this session, we shall see the chemical properties of carboxylic acids. Okay, students, actually in the chemical properties of the carboxylic acids, we have four different sets of reactions. That is reactions involving the cleavage of OH bond, and next one is reactions involving the cleavage of COH bond, and the reactions involving the COOH group, and also the substitution reactions in the hydrocarbon part. Okay. So based on these different categories, we are going to see the reactions now. The first one is reactions involving the cleavage of OH bond. Okay. So the first one is the reactions with metals and alkalis. Actually, so first reaction is the reaction with the metals and alkalis. Okay, so let us see what is happening here. The carboxylic acid, just like that of phenols, will be reacting with this metals. Okay, metals and the salts of the alkalis to evolve hydrogen. It will be releasing hydrogen. Okay, so the carboxylic acid will be reacting with the metals and also the salts of the alkalis, and it will be releasing hydrogen. So this is what the reaction goes on. So let me explain how it happens. See what happens here. This acetic acid, I have taken acetic acid CH3COOH. This undergoes dissociation first and it forms 2CH3 COO minus plus 2H plus. So the hydrogen is evolved. Okay. So we are getting hydrogen. And now what happens? This Na will be reacting with this and it forms 2CH3 COONA. That is sodium salt of acetic acid. Okay. The sodium salt of acetic acid. The sodium acetate is formed. Okay. This is what happening. Now, let us see the next reaction, that is acetic acid. It is reacting with alkali. Okay, it is reacting with alkali, that is sodium hydroxide. So let us see what happens here. See again, this gets cleaved like this. Okay, so OH combines with this hydrogen and the Na combines here. Okay, so we are getting the product like this: CH3 COONA, sodium salt of acetic acid, plus water molecule. So water molecule is released. Okay. So this reaction is little different. Whereas here hydrogen is evolved, here water molecule is released. Okay. So the next one is, see here, unlike phenol, this carboxylic acids. Okay, the carboxylic phenol will not be reacting with sodium bicarbonate. Rather, these carboxylic acids will be reacting with a weaker bases such as carbonates and also bicarbonates to evolve carbon dioxide. Okay, so this will be giving carbon dioxide. Now let us see the reaction. This reaction is used to detect the presence of carboxylic group in an organic compound. Okay, so let us see how this reaction takes place actually. See here, CH3 COONA, okay, plus water molecule plus carbon dioxide. Okay, so this is what. So this is the type of reaction. See, the next reaction is the reactions involving the cleavage of COH bond. Okay, see, under this type of reactions, we have the formation of anhydride and esterification. Okay, so let us see how it happens. Formation of anhydride, how the anhydride is formed. Okay, see this, when carboxylic acids on heating with mineral acids such as a sulfuric acid or with phosphorus pentoxide gives corresponding anhydride. Okay, so when this carboxylic acid, here we have taken acetic acid CH3COOH, CH3COOH. Okay, so I have taken acetic acid, two acetic acid molecules we have taken, and when it is heated with the mineral acid, either in the presence of sulfuric acid as mineral acid or in the presence of phosphorus pentoxide P2O5, we will get the anhydride. So anhydride means removal of water molecule. After the removal of water molecule, see here this removal of water molecule. Okay, so water molecule is removed. So here we will be getting the anhydride. So let me write the product now. CH3 C double bond O. Here we have O. One O is here, is it not? So this will be combining with this. Okay. So O. Now here C CH3 double bond O. Okay. So this is ethanoic anhydride. Okay, ethanoic anhydride. So when anhydride is formed, when an acid is heated, heated in the presence of mineral acid or with the phosphorus pentoxide, water molecule will be removed. See here, COH bond is cleaved. It's not COH bond. COH bond. This bond is cleaved. Is it not? This is broken, right? That's why this comes under this type of reaction. Reactions involving cleavage of COH bond. Okay. Now let us see esterification. Carboxylic acids are esterified with alcohols or phenols in the presence of mineral acids such as concentrated sulfuric acid or HCl gas as a catalyst. Okay. So during esterification, this I have taken acetic acid and the ethyl alcohol. This reaction takes place in the presence of concentrated sulfuric acid or HCl gas as a catalyst. Okay. So again there will be the cleavage of COH bond. Okay. So what happens? There will be a breakage here. Okay. So this OH will be combining with the hydrogen of this ethyl alcohol and it forms an ester. Okay. So you write down the rest of the product CH3 COOC2 H5. Is it not? So we have got the ester. Understood, students? Next is a reaction with phosphorus pentachloride, phosphorus trichloride and SOCl2. Okay, so the hydroxyl group of the carboxylic acid behaves like alcohols and is easily replaced by chlorine atom on treating with PCl5, PCl3 and SOCl2. Okay, so let us see the reaction how it's happening with PCl5. See here this PCl5 first it cleaves like this PCl3, Cl, Cl. Okay. So now what happens is here the breakage, let me write down the how it breaks. Okay, like this it breaks. Now what happens? This oxygen combines with this PCl3. Okay, and now this chlorine combines with this H, and this chlorine combines with this CH3CO. Okay, now write out the product now. CH3. Okay, CH3COCl. Okay, CH3COCl plus POCl3. Is it not? POCl3. Here this oxygen is going and comparing with this, so POCl3. Next, this hydrogen combines with this Cl. Is it not? So plus HCl. Okay, so this is what happening. Now let us see how this reaction takes place. That is acetic acid. 3 molecules of acetic acid combines with phosphorus trichloride. Okay, how here? Here this breaks. Okay, and here also this breaks. Now this 3 here we are having 3 molecules, is it not? And here we have 3 chlorine atoms. So this chlorine will be combining with this. Okay, all the 3 chlorines combines with this. Okay, and all these 3 OH here also we have 3 OH, is it not? This 3 OH combines with this phosphorus. So we will get CH3 COCl 3 times plus H3PO3. Okay, H3PO3. This is the product. Okay, and now let us see how this that is the last one. Acetic acid reacts with thionyl chloride. How this thionyl chloride breaks? See here, chlorine. Come on. Okay, so now there will be a breakage here. All right, and also here. Okay, 2 breaks. Now what happened? This oxygen combines with this sulfur SO. Okay, and one of the Cl will be combining with this hydrogen. Another Cl will be combining with this one. Okay, so what is the product? CH3 COCl plus here this oxygen is combining with this SO. So we are getting sulfur dioxide plus this chlorine is combining with this hydrogen. So we will get HCl. Okay. See here, these two products, sulfur dioxide and HCl, both are gaseous products. So they themselves will escape. Okay. So when you are comparing these compounds, PCl5, PCl3 and SOCl2, which is the best one? This one. The reaction with SOCl2, that is thionyl chloride, is the best because the other byproducts, that is sulfur dioxide and HCl, both are gaseous products, so they will escape. And it is easy to recover CH3COl, whereas in other cases it is possible we have to remove POCl3 H3PO3. Okay, only then it is possible to get this CH3COCl in a pure form. Understood, students? So the best method for chlorination is reaction with SOCl. Understood? Next one is the reaction with ammonia. See, carboxylic acids react with ammonia to form ammonium salt which on further heating at high temperature gives amines. Okay, so first it forms an adduct with this ammonia, that is, it forms an ammonium salt, and further when you are heating that at higher temperature, we will be getting the amines. Okay, let us see how this happens. See here, this acetic acid combines with ammonia to form a adduct CH3 COONH4. Okay. See here, this NH3 combines with the hydrogen and it forms NH4. So it forms an adduct. Okay. So minus plus. Now when you are further heating this one, when you are heating this, there will be a loss of water molecule. That is two hydrogens from here and one oxygen atom combines to form water, and water molecule is released, and you want to write the rest of the thing. What is the product? CH3 CONH2, amides. As I told you, this is acetamide. Okay, this is acetamide. Okay, so it's already given. So on further heating this one, we will be getting the acetamide. This is ammonium acetate. Okay, this is ammonium acetate. Understood? This is ammonium acetate. Okay, now let us see what happens when benzoic acid is treated with ammonia. The same type of reaction takes place here. Okay, so it forms an adduct CH3 COONH4 minus plus. On heating this, there will be a limole of water molecules, and so we'll be getting the benzamide CH3 CONH2. Okay, so we are getting benzamide. Okay, all right. The next one, see, this is phthalic acid. Okay, phthalic acid, how it reacts with ammonia. Okay, here also the same type of reaction, that is an adduct is formed. COONH4 plus minus, here COONH4 plus minus. Okay, now when you are heating this forms an amide. CONH2, again CONH2. This is phthalimide. Okay, so this compound is named as phthalimide. And when you are heating again, when you are strongly heating, again when you are heating, you will get a phthalimide. Okay, we will be getting phthalimide. Okay, so let me write the product. Double bond O, C, double bond O. Here this combines. Okay, NH. So this is phthalimide. Okay, phthalimide. Let me write the name. Phthalimide. Okay, whereas here phthalimide. Phthalimide. Okay, that's the difference. Understood, students? This is what happening. Next one is the reactions involving COOH group. Okay, so the first one is reduction reaction. See, these carboxylic acids are reduced to primary alcohols by lithium aluminum hydride or with better with diborane. Okay, so actually diborane does not easily reduce the functional groups such as ester, nitro, halo, etc. But sodium borohydride does not reduce the carbonate group. Okay, so here we are making use of lithium aluminum hydride. Either we can make use of lithium aluminum hydride in the presence of ether or diborane, that is B2H6. When you are reducing this acetic acid, we will be getting alcohol. Okay, CH3 CH2 OH. So this is the product we are getting. Okay, next one is a decarboxylation. See, carboxylic acid lose carbon dioxide to form hydrocarbons when their sodium salts are heated with soda lime. Okay, when the sodium salts are heated with soda lime, we will be getting the hydrocarbons by losing carbon dioxide. Okay, CH3COONA. So what happens here? There will be a break, right? Now this is sodium hydroxide. Here also there will be a break. So this will be combining here. Okay, and this hydrogen will be combining with CH3. So we'll be getting the product like CH4. As I told you, we'll be getting the hydrocarbon plus Na2CO3. Na2CO3. Okay, Na2CO3. This is the product. So that the loss of this carbon dioxide is released. Okay, loss of so we are getting Na2CO3 plus a hydrocarbon, that is CH4. Okay. Next important reaction is the substitution reaction in the hydrocarbon part. Okay, The first one is the halogenation, and that's a specific name for this type of reaction, that is Hell-Vollard-Zelensky reaction. Hell-Vollard-Zelensky reaction can be shortly written as HVZ reaction. HVZ reaction or Hell-Vollard-Zelensky reaction. So let us see what is happening here. This carboxylic acid is having an alpha hydrogen atom or halogenated at the alpha position on treatment with chlorine or bromine in the presence of small amount of red phosphorus to give alpha halocarboxylic acid. Okay. So carboxylic acid, this is a carboxylic acid which is having an alpha hydrogen atom, and here this is halogenated in the alpha position by treatment with a chlorine or bromine. Here I have given a 6,2, that's a general format for the halogens. So here we can have either chlorine or bromine, and this takes place in the presence of small amount of red phosphorus to give alpha halocarboxylic acid. Okay. So CH3, CH2, COOH have taken. So what happens here? See here, this hydrogen, this one, that is one of the halogen here, X is it not? So one of the halogen will be combining with one of the hydrogen, and the rest will be combining with this carbon. So we'll be getting CH3, CH, X, COOH plus HS. Okay. So this is the product. So halocarboxylic acid. This is alpha halocarboxylic acid. So this reaction is called as Hell-Vollard-Zelensky reaction or HVZ reaction. Understood, students? This is a very important reaction. So the next one is the ring substitution reaction. See, in ring substitution reaction, what happens is the carboxylic acids undergo electrophilic substitution reaction in which the carboxyl group acts as a deactivating and meta-directing group. Okay. So this carboxylic acid will be acting as a deactivating group and also a meta-directing group. That means the group which is coming inside here or trying to attach with this ring will be directed towards the meta position. That is towards meta position by this carboxylic acid. Understood? So let me write the product here. Here this is the first reaction. This benzoic acid is treated with concentrated nitric acid and sulfuric acid. That is nitration is taking place. So here we will be getting the product in the meta position. That is the nitro group will be attached to the benzene ring to the meta position. Okay. So this is meta nitro benzoic acid. This is meta nitro benzoic acid. Okay. And next we are this benzoic acid is undergoing bromination in the presence of Br2 bromine and FeBr3. Here also it is meta-directed, so we will be getting the product in the meta position. Okay, that is substitution in the meta position. BrCOOH. Okay, so meta-bromo benzoic acid. Meta-bromo benzoic acid. Understood, students? Well, fine, students. I hope you might have understood what I have taught today. Let me meet you with another important topic in my next session. Until then, it's Dr. Anita Raj, your chemistry mentor, signing off from you. Thanks for watching.